Dear students, Assalamu alaikum and welcome to the course of Wireless Sensor Network. I am Dr. Zishan Bangish, Assistant Professor, Institute of Computing, Kohat University of Science and Technology, and today we will be talking about sensor network programming. Since application development for sensor network differs in many ways from programming traditional distributed systems. So here we will be discussing about the challenges for a sensor to be programmed, then some constraints that are involved for node-centric programming, keeping in view the language platform and the operating systems for sensors. And then we'll be discussing an example how to program using Nessie, and at the end we will summarize our today's discussion. So let's start with the challenges for programming a sensor. So if we consider different examples that includes continuous interaction of sensor nodes with their physical environment, so the stringent constraints of sensor node, the ad hoc deployment of many sensors, the frequent changes in the topology of network, and particularly the mobility and the failure rate. So these are some of the challenges that make this type of network different from the other traditional networks, or particularly the wireless sensor network. From the developer's perspective, the goal is basically to design and program a reliable and efficient wireless sensor network, and that can cope with the dynamic and uncertainties in the sensor system. However, from a user's perspective, the network is often viewed as a database, where user interacts with the sensors through queries and the receiver response in a reliable and an efficient way. So there are different challenges in a WSN programming model. So let's talk about these challenges. So the different challenges to be discussed during the current session is the reliability constraint, the resource constraint, the scalability constraint, and the data-centric networks constraint. So let's talk about one by one in detail. So the reliability. Wireless sensor networks are unreliable than the distributed system, and that's a fact about this type of network. Sensor networks are built to adopt dynamic changes and nodes and link errors such that network continues to serve its purpose even when part of the network or some nodes are not working. While many faults in the network will never be noticed by an application. So these are some of the constraints in wireless sensor network. The reliability is one of the main constraints. The second constraint is the resource constraint. So we have a very limited memory, storage, battery. So the resource limitation affects the maximum code size to be written and the performance and the memory storage capacity. Similarly, the programming environment should allow programmer to opt for the energy saving techniques. So this is again the main concern. Thus, energy efficiency is particularly critical in WSNs, and it penetrates in every aspect of sensor network design, whether it is from duty cycle to a routing protocol or to in-network data processing capabilities. So it is penetrated in every aspect of sensor network. Then the third challenge is the scalability challenge. Sensor networks can be very densely deployed. So it can be deployed in thousands. So this is the main concern. If we keep in view the programming considerations, so it's a densely populated network. So scalability is another main concerns when you're going to program for this special type of network. So manual configuration, maintenance and repair of the individual sensors will be infeasible because of this type of network. Therefore, there should be some self-management and self-configuration mechanisms that needs to be incorporated in the application. And another concern is the data-centric network constraint. So, in many wireless networks or wireless sensor networks, not only are the individual sensors are of interest, but also the data that they generate and they disseminate, that is also equally of important. So sensor network applications are therefore more concerned about obtaining useful information in a very timely fashion. So whether it is an irrelevant information in which sensor node generate this information or a valid information, so it needs to extract that information in a very efficient way. So these are some of the concerns. So let's talk about the type of sensor network programming, which is node-centric programming. So node-centric programming under the node-centric model is basically an programming abstraction. And it focuses on the development of sensor software on a particularly node or at a particular node level. So the overall network-wide sensing application can be considered as a collection of pairwise interaction of different individual sensors. Similarly, the network sensing task is a pairwise interaction of sensor nodes. So this is something that is related to the node-centric programming. Now, what is Nessie? It's basically an extension to one of the most popular C programming language, and it provides set of language constructs to implement code for distributed embedded system, for example the modes. Nessie addresses the unique challenges of WSNs. So it's basically designed for this special type of network. For example, some activities in the sensor network like message transmission or a sensor acquisition or arrival, they're all initiated by events such as the detection of change in the physical environment. So these events may occur while a node is processing data. So when we are talking about the application or a node-centric programming, so it comprises of the tiny operating system along with the Nessie programming language. That two things needs to be combined to develop a node-centric program for a node or a sensor. These nodes are very resource constrained and are very much prone to hardware failure. Therefore, the programming languages for sensor node should take these concentrations uh, characteristics into consideration, and Nessie is basically designed for this purpose. So the application of Nessie consists of some different components, and each component have a provide and uses interface. A provide interface in Nessie is a set of methods that are exposed to higher layers. So the interface is basically, it describes the use of some kind of services, and the provide is basically some methods that are exposed to higher layers, and then uses are again some set of method calls that hide details of the lower layer components. So an interface basically describes the use of some kind of services. For example, if you're going to send message, so it is done through some interfaces that has been dedicated for sending message. So let's consider an example. So the example is related to the TinyOS timer service. So this example shows that the definition for the timer, the STD control, the clock send, and the sensor, which is an ADC interface. Now, the timer interface defines two types of commands. One is the start command, and another is the stop command. And similarly, the timer interface further defines an event. You can see in the example that has been shown, which is also a function. So while commands are implemented by the provider of an interface, we have already discussed what is interface, what is provider, what are users, what are uses. So we have already discussed about that. So when a commands are implemented by providers of an interface, so the events are implemented by the users. So similarly, all the interfaces in this example have been defined by both commands and events. So you can see this. Now, apart from interface specification, the components in Nessie also have an implementation as well. So the modules are components that are implemented by the application code, while the configurations are components that are implemented by the connecting interfaces of the existing component. So that's important. So I repeat that the modules are the components that are implemented by the application code, while configurations are components that are implemented by the connecting interfaces of the existing component. So Nessie application has a top level configuration that describes how these components are wired together. So every Nessie application has a top level configuration, and we have just discussed that these how these components are wired together. So consider some functions like commands and events in Nessie. and that have been described as f.I, where f is a function in an interface I. So the functions are invoked using the call operation. And the functions are also invoked using the signal operations if in case of events. So the call operations are used for commands and the signal operations are used for events. So here's another example that's related to a sensor application that periodically obtains sensor readings. So in this example, the std init is called, you can just look at the code, it's called at the booting time. So the timer expires when it's been called after 1000 milliseconds. So upon time expiry, a new sensor sample is obtained by again calling adc.getData, which in turn triggers the actual sensor data. And this triggering is done through adc.dataReady. So in Nessie, or we can say that in the tiny OS, which is the operating system for the modes and sensors, the code either execute asynchronously, that is in response to the interrupts, or it is executed synchronously, that is it executes as a scheduled task. So asynchronous code is basically that it is reachable from at least one interrupt handler, whereas the synchronous code SC is reachable only from tasks. So this synchronous code is always atomic to another synchronous codes. So it's executed sequentially and it executes without any preemption. So this is very important. So about the race condition. This race condition occurs when there is a concurrent updates to the shared states that have been performed. So whether either this shared state is modified from the AC or the shared state is modified from the synchronous code that is also modified from the asynchronous code. So these are some important points, keeping in view the node-centric programming that will be discussed later on in the coming lectures when we will be discussing some more code about node-centric programming. So we'll be discussing the asynchronous codes and the synchronous codes and also about this race conditions. Synchronous code is always atomic as already discussed because tasks are always executed sequentially. However, the race conditions are possible only when shared state is modified from AC. We have already discussed that as well. Therefore, the Nessie provides programmers with two options for atomicity. So the first option is to convert all the shareable code to tasks, that is to a synchronous code. And the second option is use atomic sections to modify shared state. So the Nessie will always run automatically. So atomic sections are indicated whether the keyword which indicates the block of statement should be executed atomically, and that is again without any preemption. So we have already discussed that the Nessie provide two options to ensure atomicity. It converts all the sharing code to the tasks, and again it uses atomic section to modify share states. You can just look at the portion of that code. So a preemption can be obtained by disabling the interrupts during the atomic section. So these are some important considerations that needs to be kept in mind before programming a node, if it's a node centric programming. So we talked about this. So we have discussed challenges, and we have discussed about the node centric programming. So node centric programming is basically the abstraction of the language, and tool focuses on the development of sensor software on a per node level. So we discussed about some challenges for the sensor programming that comprise of reliability, the resource constraint, the scalability, and the data centric networks. And we talked about the different considerations of the TinyOS and the Nessie, keeping in view the programming constraints. And we have come across a consideration that the sensor nodes are very resource constrained and are very much prone to hardware failure. Therefore, the language that has to be used for sensor nodes programming must take these things into consideration. So Nessie is basically designed for this purpose. And about the TinyOS, that code executes either asynchronously or synchronously in TinyOS. So the race condition can occur when the concurrent updates are there to share states. So with these come to the end of our today's discussion. So we'll be talking more about the network programming. These are the references from which the data has been taken in the current slides, in the current presentation. So thank you very much for listening me, and for regular updates, and for watching our lectures, upcoming lectures. So subscribe our YouTube channel by clicking the bell icon. Take care. Allah Hafiz.